All right. So, hello. Um, this is Ada from the Pond, and today with us is Thomas Goorden. And I'm super happy that Thomas agreed to do this session for us because I saw his talk at the Arena Climate Conference in October in Budapest, Arena Climate Conference. And I really loved it because it was super nerdy. And I haven't seen a talk like that at any journalistic conference before. So I think it actually deserves to be done again and then recorded and put out there for people who might want to use this method and um, who might want to do their own CO2 calculations because that's what it's going to be about. So I am going to now give the floor to Thomas.
Hi. Hi, Ada. Lovely to see you again. Lovely to see Yella here as well. Yeah, so I'm just going to run a little bit through the workshop I gave back then. Um, and of course, I have to start with a little bit of background. So I have a training in physics, actually. So journalism is a very late calling for me. And in between, when I studied physics, which I never did academically. Uh, in between that and becoming a journalist, I did a lot of programming. So it kind of explains why I'm really into this because I'm combining all this understanding, these skills together in what I'm doing now, which is investigative journalism on environmental topics. And you already said carbon. So we will talk about carbon a lot, and obviously that is because climate is hugely important when you're in a climate discussion. When we talk about climate change, how the impacts of it, but mostly like how it's happening, why it is happening. But I do want to stress that actually a lot of the techniques here are valid in many environmental aspects as well. So I use this in PFAS research, for instance, which isn't directly tied to climate or carbon, but you can do mass balance equations pretty much in anything where you are dealing with physical substances, chemical industry, large masses of things that are moving. That's a very generalistic thing, a way of thinking about it. But you could also use it for things like energy calculations, which is like another area. Maybe you're working on data centers and you're thinking about water usage or electricity usage. Is a topic that a lot of people will be working on. The basic techniques here are usable in those contexts as well. Anything where you have physical parameters, you're trying to figure out what is going on here, and I want to do some basic checking. Like, does it make sense what they're saying here? How big is this compared to something else? That is the basic of it. To a certain extent, it's also really high school physics and high school chemistry, but done in a way I think that is relevant to what we need as journalists, investigative journalists. So what I talk about is things that you will also see in governmental reports sometimes or scientific reports. It will help you kind of do very basic checking. It's not really going to allow you to make a big physics paper or chemistry paper. You'll need to do a lot more work than that, but it can help you make sense of things and do double checking, which I think is actually our most important task, is to fact check. Maybe I can show my screen. Is that an idea?
Yes, please.
Yeah.
Mhm.
I have to allow something here. Um,
Yeah,
okay. Yeah, that's good. I
we
can
see it.
probably make it
Yeah.
bigger, but let's see if we can. Tell me, is this good?
Yeah, you can make it a
You
tiny
want-
bit bigger still.
Sure.
Yeah. Yeah,
Yeah.
this should be fine. Yeah. Hmm.
Okay. Here we go. So we are in a notebook. For people that don't know this, it's not a core topic, but a notebook is kind of like a document with a running calculation inside of it. It's like you're writing software, you're writing little scripts, and in between we can write text or we can put images or a lot of other things actually, which I will demonstrate. There's many ways of doing notebooks. Very well-known one is a system called Jupyter, which you can find online. But you also have Google Colab, for instance, which is online, Google infrastructure. This is running locally, and it's called Pluto. Pluto is a notebook technology that we run inside of Julia. Again, something new because Julia is a programming language, a programming environment. It's very comparable to any other, like Python maybe, but Julia has very peculiar things that I love a lot. The code should be easy to read. Actually, there is a GitHub link for this one as well, which we'll share, I'm presuming. Um, Basically, to start this, I had to pull up for people that want to know. You have to basically get into a Julia prompt. You have to activate Pluto and then run it. And then you get a local server, which pops up and gives you the option to open a notebook. I won't go too much into it because, it's a bit boring. But you start Julia, you start Pluto, and you start your notebook, and then we can start doing lots of things. What I'm showing here is actually not code, it is Markdown. And so basically, what we see on the bottom is the code that results in the part on the top. You have to flip every block upside down. So the code is on the bottom, and when we execute it, we see the result on the top. And we see that this is, of course, just Markdown like you would have in Wikipedia, maybe, or other places. It's just text, but the text gives us like nicely formatted results. This is also useful, I think, if you want to do something where you want to show your work. This is something we do in publications sometimes, show your work. What I did with this was actually to make a PDF that we attached to our investigation that showed the entire mass balance calculation as a nicely formatted PDF with basically everything in it to reproduce it, which I think is very powerful. And actually, you could share the code as well, so people could rerun the calculation and do other stuff with it. We can hide the code and move on. And then we'll very briefly talk about what Julia is as a language. So to do that, we need what we call a code block. It always has a beginning and an end. This is what we execute. And we could do basic things that you know from other programming languages, like do a function. Julia is very mathematically oriented, which I like a lot. It's one of the things where a lot of times things that we know from high school math, basically the way you write that will be very similar to what you see in Julia code. So it's a language written or developed by mathematicians mainly, and it shows. So it doesn't, if you come from other languages, it shouldn't be too difficult to learn it. But sometimes you're like, how? Whoa, this looks more like math and programming almost, and that is the reason. So here you can see we do a function, and we can execute that function. I have an example here, but I already do a major trick here, and that's this hand calcs thing. Because there's an at in front of it. It's basically meta programming immediately, which means that this hand calcs function, which is underlying it really is, it actually operates on the code itself. So here is the normal code, just in blue, but the hand calcs thing takes that code and does something else with it, a meta programming thing. And what does it do? It actually shows the code in what I would call high school mathematical notation, which means that suddenly we flip from writing code to writing math in a way that I think anybody who did high school math would be able to read. So, like, oh, yeah, this is what I remember. And this is the reason why I do it, because that means that I'm doing an actual programming calculation here. But if you don't know how to program Julia, you can still follow along by just reading the math, because this is the universal language, right? And so that's already pretty nice. All right. So we know we can execute code. We know we can show it in a mathematical way, so you don't need to have to read the code. And then we can start using it. And we already talked about a little bit. We're going to talk about carbon cycle. You have to stop me here because I can give a whole lecture on this slide alone, or this image alone. But the basic idea is that the problem with climate change, summarized from a physics perspective, is that we're taking carbon from deposits that have been there for hundreds of thousands, millions of years. We're pulling up the carbon, the atoms, the carbon atoms. We're doing lots of stuff with it, but in the end, we mostly burn it, and then it gets combined with oxygen to make CO2. That's a major thing, carbon dioxide. And this is a greenhouse gas. And so slowly we're pumping carbon up into the atmosphere in the form of carbon dioxide, and we're adding a greenhouse gas. And this is climate change, really summarized. We can make it a bit more difficult and say, yeah, but some carbon dioxide is taken up by plants. And then, yeah, but we also burn and eat those plants. So it goes back up. So there's the carbon cycle, which is natural. The carbon cycle, we don't really worry about because, the earth just breathes carbon constantly. The problem is that we're adding way more carbon than was here during human times. That's the other thing to know. Yes, there have been times on this planet where there was more carbon dioxide, more carbon on the surface, but it was trapped millions of years ago. And now we're untrapping it and we're reverting back to that time, which was a lot warmer than our entire biosphere was designed for. Well, not designed for, but evolved towards. So that's a problem. Which means that we really want to keep track of the carbon. And if you think about carbon reporting, and when we think about the fossil fuel industry, the way I think about it is really it's about carbon transport and where is it going. A lot of climate reporting is purely focused on emissions. But you could argue that if there's no extraction, if we're not taking carbon from the soil, emissions actually don't matter that much. And this is a really weird thing, but it's very fundamental. That's why we say, for instance, that burning wood is climate neutral, because it's part of the cycle. The carbon theoretically can go back into wood, and then we can do it again and again and again. But this is not true for fossil fuels. And so tracking fossil carbon is basically the same thing as tracking the danger to our climate. It's the same thing. The more carbon we extract from the earth, the more will end up in our atmosphere and the hotter it will get. So we're
Could
trying
you?
to punch through that.
Can I have a
Go ahead.
question? I have a question. Like when
Sure.
you say the fossil fuel carbon, what are we talking about? We're talking
Yeah.
about gas and diesel and plastic, but is there anything else that?
Well, well, plastic actually isn't fossil fuel. It's a derivative from fossil fuel. What it really is, it's coal,
Hmm.
oil, and gas. Anything coming from below. And we'll talk about actually, from my perspective, they're not even that different. And you'll see why.
Okay.
They're almost the same. They're pretty much the same thing, but just in a slight variation. All of it is, that's also why it's called hydrocarbons. Hydrocarbons is encompassing all of that: natural gas, ethane, propane, butane, any kind of oil, gas to diesel, any heavier oil, cars, and then we get to like more solid things, which would be coal.
Hmm.
Uh, Actually, even diamond, technically speaking, can be considered family of hydrocarbons. Did you know that diamond burns?
No.
Yeah, if you have a house fire, your diamonds will evaporate. All that will be left will be gold.
Wow.
Yeah, you didn't know that? Yeah, that's a well kept secret. But if diamond gets hot enough, it just burns. It'll be gone because it's essentially carbon. Yeah. See your shock. It's yeah. Welcome to
I have
to
no
science.
diamonds, so I'm kind of now
No,
I'm
no.
I can rest. I can rest.
Yeah. So what we're gonna ignore is for this presentation is methane emissions, even though there's carbonates, but it's actually not that. It's not as big of a deal as CO2. We're not talking about nitrogen or fluoride gases from the PFAS industry, which are also greenhouse gases. Lots of things can be a greenhouse gas, but the dominant one is CO2. And the reason is because of the amount of carbon that we're pulling up. It's just really about how much is there below the surface and how much we're pumping up. And we're definitely not extracting as much fluor from fluor mines, for instance, as we do from places like Qatar, which is in the news today, and so on and so on. So why are we worried about it? I mean, this is preaching to the choir, but thinking of it from a mass balance perspective, the only thing I really care about is the carbon budget. Because the carbon budget is actually kind of what I would dub Earth's thermostat. It is kind of like this really big social collaborative decision, even though there's nobody really deciding on how hot we want to make this planet. Because the more carbon we actually add to our atmosphere, the higher the temperature will get. It's as simple as that. Now, of course, we cannot predict entirely where we're going to end up. That's where it gets a bit messy. That's why climate scientists talk about likelihood. They say, okay, let's say you want to have a 50% likelihood of staying below 1.5 degrees Celsius. Then you'll get a carbon budget, and then when it will be exhausted. This still needs to be updated, but actually, yeah. So if you only need a 50% chance of 1.5 degrees Celsius, which is the Paris Agreement, then we know that at the current rate, it will be exhausted in 2028. I can already tell you this is too optimistic. It's probably going to be 2027 already.
Mm.
But let's slide this up and say, like, we want to be pretty sure that we stay within 1.5 degrees Celsius, 83% chance. Well, bad luck. It's already too late. We already crossed that line in 2025. Right? So, which means that actually we start looking at 1.7. The exhaustion rate is very, very rapid. The 83% chance of 1.7 is already exhausted in 2032. And 2 degrees, which I find extremely shocking, is already in 2042, which is actually around the time that net zero should be reached. But we'll just speed past 2 degrees Celsius in what is it, 15 years, and it's going really, really, really fast. And so you have to make everything all right in your head. You have to like, oh, a 50% chance of 2 degrees is fine. It's a toss. And also remember that means that the chances of 1.7 will definitely be exhausted already. So it's not like, oh, we have a chance of 1.5. No. We're already past 1.7. What is the chance that we also passed 2 degrees? It's still ridiculously close,
It
right?
is, yes.
And this is the reason why we want to keep track of how much carbon is being extracted and being pumped and gone through all kinds of systems. Which actually I think we're very on topic because the oil and gas prices is like a really big thing. And all I'm thinking of is that if you think about the carbon budget, the more it crashes, the safer we are. Economically, of course, it's a disaster. Yeah, sure. And it has a wildly negative effect on people's lives. But in the long term, the extraction of oil and gas has a much, much or terrible thing. Anyway, I pulled up another science bit. Let's be more fun. Mendeleev's table again, high school physics, but or chemistry. But what we're really interested in is this one over here. And why is this Mendeleev table actually important? Well, it has this little number here, which we call the mass of the atom that we're looking at. In this case, 12 grams per mole. Of course, the real mass expressed in our in our scales would be extremely, extremely small. So basically, this is 12 grams of a whole lot of atoms, like 10 to the 23, 23 zeros, a lot of carbon atoms before you get to 12 grams. But it's just a shortcut we use so we can have kind of, measurements that make sense to us. But the interesting thing is we can see that carbon is way, way lighter than hydrogen, for instance. It's 12 times heavier. That's actually quite a lot. And the other thing, because we talk about natural elements, so elements that occur a lot naturally, the other one we're interested in is oxygen. Is it missing? Oh, no. Here we go. There's more Mendeleev. Oxygen is 16 grams per mole. So it's actually heavier than carbon. And this is cool to know because it solves kind of a weird paradox, something that seems like a paradox, but it isn't. Nitrogen is in there. So we can calculate with these masses. And we're going to do that in a very simple way. But actually, I want to already say, like, if your memory is good enough to remember these three numbers, well, actually, six numbers, we're already fine. You just have to remember how heavy hydrogen is, 1 gram per mole, carbon 12, and oxygen is 16. If you know that, you don't even have to look at the Mendeleev's table because you could do this entire calculation off the top of your head. It's pretty cool. The other thing that you need to know is the number of bonds. So basically, connections with another atom that these substances can make. These atoms can make. Hydrogen can only make one friend. Carbon can make 4 friends. It can also have what we call double friends, double bonds. So it can hold hands, 2 hands with one atom, right? That's a double bond. So it uses up 2 of the 4. So it can have 2 really good friends. It has 4 arms. Oxygen can have the same thing, can have a double bond as well, or 2 separate bonds. And that already allows us to understand carbon dioxide, our most worrisome molecule. Because what is carbon dioxide from a chemical perspective? And I'm going to sound really stupid saying this, but it's a carbon atom that makes a double bond on both sides with one oxygen atom. So it's a double friendship on one side, double friendship on the other side, and everybody's happy. All the connections are made. The oxygen is happy. It's fully saturated. Carbon is fully saturated. That's the way we talk about it. And this is our molecule. And here we see a little Julia trick, and you're like, what the hell is he doing there? Well, for people that, oh no, don't do plus. I want to see what's in here. So you see, I have a little function here called molecule, and it accepts a string, a Smilis string, which is actually a notation that you'll find a lot to describe atoms in PubChem, for instance. You've probably seen this. But the cool thing is that these Smila strings are basically just text descriptions of molecules, and we can use a library to show them. So I just dump this string into another function, which gives me kind of an object. We can do a little trick here. Not in this case, there is no hydrogen, but if there's hydrogen, usually they hide it, but we want to show it. So I say, show me the hydrogens. And then I just return it. And funnily enough, Julia knows, like, oh, wait a minute, you're giving me this object that you created here, but how do I render this? And this is where Julia really shines, because every library can give Julia a option of how to render it, and it just folds into the notebook, and boom, it shows us a molecule. So there's no, there's no extra libraries that we have to add to do this. It just figures out, like, oh, you want to show this somehow. Do I have an option to display this? Yes, I do. I'm going to use it. Boom. And we don't have to do anything else. And this really has to do with how the language works. Okay, we've shown a carbon dioxide molecule, but how heavy is it? Well, we know, it's a carbon and two oxygen atoms. So it's just 1 plus 2 times the other thing. And we can just calculate it here. And this is something we're going to dive a little bit into this data because I think this is probably the main reason why I use Julia. And it's not this sum, because you can do that anywhere, but it's this thing here where I use units inside of my code. Remember, we had this atomic mass in the Mendeleev table, and it's expressed in grams per mole. But the problem is that maybe I had another source for the carbon, and for the carbon, it was expressed in kilogram per mole. Now, what happens if we start calculating with those kinds of numbers mixed together? Well, we start making mistakes. We start making what we call unit mistakes. And the most simple is, mixing the decimal points, because we're using kilo or mega or tera, something like that, combined with one of the other ones. But the problem is we're shifting our decimal constantly when we do that, usually by a factor of 1,000 or a million or a billion. And it can give wildly incorrect results if you're not paying attention. Now, people might say, yeah, but I'm careful. And sure, you're careful. I'm careful. I could do this in any programming language. I could do this in Excel. You can do this in a spreadsheet. But the problem is you're having a bad day, or you get distracted by a colleague for 5 minutes and you forget that you used a different scale in the unit system and you're screwed. And actually, there's a very famous disaster with I think one of the Apollo programs, where they mixed the U.S. Imperial system with the metric system without noting it, and they had disaster. It wouldn't have happened if they used this. And why is that? Because I'm using a library called Unitful, and it allows me to actually express my numbers in a unit. And that's what I'm doing here. So I'm basically saying, yes, I'm working with a number. I'm going to calculate. But then I add this little u, so the code knows, oh, he's doing a unit. And then I express my units as a string. That's it, really. And if Unitful knows the unit, it's super happy. It's like, oh, I know what this is. I can work with this. And from now on, you can use this thing, what you would call a number with a unit, in any calculation. Any function in Julia will just work. We don't have to redefine the multiplication or the sum. That's already been done for us, which means that we can actually add two things with units, or we together, or we can multiply something with a unit by 2. And this is actually way more magical than you would think. And the real power here is that underneath the hood, Unitful, this library that we're using, is solving our problem that we mixed our units. Because if we look at the calculation here, we see we used kilogram uh, in one case and gram in another case, but it just converted to grams. It knows that kilogram is 1,000 times 1 gram, so it will just convert and make sure, which means I can trust my output. I don't have to check. I can just look at this and go like, oh, my input in units are correct, which means that the output of the calculation will have the correct unit. The only thing I do here is basically specify what I want to see, but I could change this into kilogram and it's fine, right?
Mm-hmm.
We can. This is the other useful thing. Sometimes we're like, oh, this number is really big. Let's make it kilo or mega or something like that, and make it easier to read. And we can just do it like this. We can ask, oh, make sure that the output is in this form, and it'll just do that. So again, if you don't remember anything else up until after this, it's already super useful. Work with a unit library and stop making unit mistakes. There, actually, you shouldn't, because there's a way to completely, forever avoid it. Right?
So
And I
is
can
this
tell you, yeah.
is this like
Sorry.
if we only calculate we're gonna get to calculating like the emissions, right? But there
Yeah.
actually you only have the mole weight for the two atoms, as I understand it, right? Which you need to work with.
Yeah. Yeah.
And if you'd put that in the moles, like in the grams per in the mole per grams,
Gram per mole.
oh sorry, gram per mole.
Yeah.
um, what is the unit mistake that you can make? Because that's something that you can set, right? Like this is the
Well, what
carbon. Hmm.
what you could do, so what naively people might do is, let's see here, mistake. So let's say I forgot that actually my source of the molecular mass of carbon was wrong, was different, was in a different unit. You might end up doing something like this, right?
Hmm.
You're like, oh, okay, this is in grams per mole, but this was actually in kilograms per mole.
Hmm.
But you didn't really see it, and you end up with a number, but how nothing will tell you that you made that mistake, right?
Hmm.
This is the problem. So you thought you were maybe dealing with kilowatts, but you were actually dealing with megawatts.
Hmm.
Boom, you're
Hmm.
done for.
Hmm.
And especially if you mix that, and in reality, if you think about journalism, almost every report you will encounter will be in different units,
Hmm.
right? The carbon budget, if we pull it back up, is a very peculiar one, because the carbon budget is in gigatons,
Hmm.
gigatons of CO2. Now, you have to be really, you can easily make a mistake. Like, how much is a gigaton really? Could you tell me? Like, how many zeros? You would have to look it up in a table, and if you make any, or if you're a bit too confident, then suddenly you're making a mistake on the carbon budget. Because
Hmm.
the problem is that if we think about a factory, it might have a megaton. Like, how many zeros is difference between a gigaton and a megaton? And my answer is, I don't think about it. I just write gigaton and megaton, and I look what the calculation gives me, and and I trust the computer,
Hmm.
because I know it. I told it that these are different units,
I see.
right?
So the lesson is actually wider than just this, right? It's just
Yes, yes,
hmm.
it's much wider. Yeah,
Yeah.
I'm just using kind of like a silly calculation here,
Hmm.
because why would you calculate it? Although we are actually going to use the molecular mass of CO2, it's a useful number. It's good to know. But I'm showing the code because it's so much more
Hmm.
powerful for anything else.
Cool.
Okay, let's burn methane. Methane burning is a chemical process. So we're going to convert chemically methane to CO2. And we're going to think about the atoms while they're doing that. And to do that, we're going to need to know how heavy methane is. And methane is the smallest hydrocarbon. Now, this is a bit weird as a molecular drawing. Normally, with hydrocarbons, I mentioned this before, we don't really show hydrogen. But the problem is we also don't write the C. Usually, it's just lines between the C's that we show because it's assumed that there's a carbon atom here. So we get this thing where it's hiding the C for carbon, which is in the middle, but we force it to show the hydrogen. But in reality, there should be a C. It's a carbon atom with four friends, and all of them are hydrogen atoms. That's methane. It's the smallest hydrogen atom, hydrocarbon that we have. How heavy is it? We can do the same calculation. We could say, okay, we do the mass of carbon plus 4 times the mass of hydrogen. Now, it dumped it into kilograms here, but we can do a unit conversion because we are in that world and put it back into grams per mole, right? And if you're paying attention, you should already see something pretty peculiar. A methane molecule, even though it has 5 atoms in it, is a lot lighter than a carbon dioxide molecule because it's 44 grams per mole, which only has 3 atoms. Now, I gave a hint why. Do you know why? Why is carbon dioxide so much heavier than methane?
Because
It's
hydrogen is lighter, no?
the hydrogen is lighter than what?
Than oxygen.
Oxygen. Yeah, oxygen is a very heavy element in our story. And this is weird because if you think about it, if you have a ton of methane, right? Or let's do it in a much easier way 16 tons of methane. How many tons of CO2 will that produce?
I'm not good with math from my head.
Well, so there's no math. That's
Oh.
the trick. That's why it's a trick question. So the
Oh
thing is,
no.
for every carbon atom that goes into the incineration, one carbon atom must come out. Now we know they go in as methane, so it has to be a carbon here. And it goes out as CO2, so it has to be a carbon atom inside of a carbon dioxide molecule, which means that for every, and now we're showing both, for every methane molecule, we make one carbon dioxide molecule, which means that for every 16 tons of methane that we burn, we make 44 tons of CO2.
Makes sense.
And this is the thing that I think a lot of people intuitively don't understand. It's not a paradox, but it's actually because we add so much mass from the oxygen.
Mm-hmm.
The reason why the output of a factory can actually be higher than the input is because there's a hidden input. And the hidden input is oxygen that is being pulled from the atmosphere during the incineration. Boom. Right? And this is important to know because it means that if you think about an LNG tanker, and somebody tells you like, yeah, there's 10, I don't know what's on there, but 10 megatons of LNG on there. I already know that we could very roughly it's probably about 3 times, I would say, the different very roughly 3 times. So there's 10 megatons of LNG on there. Well, that's 30 megatons of CO2. Boom. We didn't use anything else. We didn't need really all this fancy stuff to do that.
Mm-hmm.
You could do by hand. if you remember the atomic mass of these elements, you could reproduce this idea.
So
But yeah,
you actually can develop an intuition about this, right? As you,
yeah,
yeah.
yeah.
Hmm.
And this was usually important in our investigation as well. We were looking at shale gas, and basically I was counting, you know, how much gas is being transported across the ocean, and then what's happening to it. But this mass is directly equivalent to an emission, which means that we can relate fossil
Mm.
extraction directly to fossil emissions by doing this really simple calculation. And I'll repeat it because it's important to understand. We'll do it again, but this time, we'll really calculate it according to the book, and we'll say, okay, 1 ton of methane, we're going to incinerate it. We know that 1 ton of methane gives us an X amount of carbon atoms. And this is the way chemists normally do it. Basically, we count the number of carbon atoms inside of the fuel. We don't really care about the hydrogen. And this is going to be important later. But we basically say, like, okay, what happens if we just look at the number of mole? Mole is a number of atoms of carbon, which is the same thing as the number of methane molecules. Each one has one. So kilomole is a very big number. It doesn't matter. We can use this because we know for every molecule of methane we make, we also make one molecule of CO2 because there's this 1-1 relationship between the carbons.
Hmm.
So we can multiply it in the other direction because we know now how many CO2 molecules we're going to create. And this is going to tell us how many tons of CO2 burning methane is going to produce. Now, I have to make a caveat here. If you look at mass balance equations from the industry life cycle analysis, you'll often find numbers that are a bit lower than this. And the reason is because there's this assumption that not all methane will get incinerated. Okay, fine. But it's a bit silly, I think. From the perspective of what we're doing, trust me, this is precise enough to really talk about the impact of methane. This life cycle analysis, approach that you see a lot, personally, I think is bullshit. Yeah, it's bullshit. Because they're adding these little discounts in there. They're trying to add precision to it. But the question you can ask is like, yeah, if you're not incinerating the methane, what's happening to it then? And the answer is, well, probably bad shit anyway, because methane also has greenhouse properties, or maybe it gets incinerated somewhere else. Does it matter? No, from our perspective, no. Uh, what we do care about is how much carbon is actually in the fossil fuel. So what you shouldn't do is say like, oh, they're pumping up a megaton of something because oil can have lots of components. It can have nitrogen in it. It can have water in it. It can even have helium in it. So I don't know if you read this, but Qatar's LNG, for instance, has a lot of helium in it. So the thing they bombed yesterday isn't just like really important for the LNG supply, but also for the helium supply. So it's a big problem for semiconductors, for instance. Yeah. So, even if you're doing research on semiconductors and you're doing the supply chain there, this could help you because we can figure out how much helium is being extracted and so on and so on. So we did it in this case using moles, which is like um, typical chemistry way of doing it. The other way of doing it is to calculate with something called the carbon content. And the way to think about carbon content is to basically say from any substance, the mass of any substance. So you take any object, I don't know, like this piece of paper, right? What is the carbon content of this piece of paper? And it's basically a percentage, and it's going to tell us which percentage of this mass is a carbon atom. That's it. And with that idea of the carbon content, which is actually the carbon mass in terms of carbon atoms, we can do the calculation as well. I'll leave it to the viewer to work it out, but it's fairly straightforward. But we're calculating a percentage here.
So
So
every material or every substance has a certain carbon content that you can look up
yeah,
somewhere, and then you do the calculations with that
yeah,
data.
yeah. And then why is it doing here? So I'll simplify it. Oh, this is interesting. What does it want to do? Okay. Unit. There we go. So we do the same thing. So the carbon content, we could even say the carbon content of CO2 is 27%. Sounds completely weird, but it's true.
Mhm.
Right? Makes sense?
Yeah. Yeah.
We could do the carbon content of methane. Well, it is abbreviating it. That's unfortunate. How do we do that? Let's try to do it in no units. Here we go. 75%. So methane has a carbon content of 75% or 0.75. So no units, by the way, is when we divide certain things, there's no more units. A percentage is a classic no unit thing. We have to tell the library to do that. Otherwise, it attempts to stay within the unit category. You could also do a incineration factor, which I do mostly. And what I do is actually I take the relationship between CO2 and our fuel, in this case, methane, and I calculate a number that's going to tell me how much CO2 will be coming out of this particular fuel and some multiplication factor, which means that we now know that if we have a ton of methane and we multiply it by 2.75, that's how much CO2 there is exactly. Remember, I said it's about 3? Well, this is close enough to 3, 2.75. Yeah. The reason why you do these factors is because if you have a lot of different fuels, for instance, you're looking at maybe plastic and coal and all kinds of different things. They will have different incineration factors. If you want to be imprecise, just use 3 because that will work for any hydrocarbon. If you want to be precise, you can do the incineration factor per fuel, and then just multiply your inputs. Works just fine. Right?
We have about 10 minutes still, just so you know.
Okay.
Yeah.
Okay. Well, we're not too bad. So we're quickly gonna go for all hydrocarbons. So I made a little list here of all the hydrocarbons that we know based on how long they are. Oh no, pull it out here. Yeah. And so we give them names, and it's actually, goes methane, ethane, propane. And I have a slider here normally. Yeah. So we're going to look at them. This is now an interactive notebook. The trick I did here was make a slider, and I bound the slider to this number n. So that's going from 1 to 20. That's what I'm doing here. and I can change it. I can make it N1, 2, 3, and so on. And then I have this little molecule here. It's generating a bunch of C's, a bunch of carbons, depending on where we are, 1, 2, 3, 4, and so on. And then I'm saying like, render me the molecule. That's it. And that's how we're able to show the molecules. We're doing ethane, that's propane, butane, and then we get to the lighter oils. This is probably about 8. So it's octane. This is actually gasoline, mostly. Gasoline is mostly this. And then we go up, and then we go into heavier fuels, which would be diesels. If we keep going up, what do we get? If this string, this molecular string, gets longer and longer, in the end, actually becomes tar, but also plastic. Plastic is a very long hydrocarbon, which means that we suddenly discovered a magical way of burning plastic. Now, and the magic about it is that actually it's the same thing as burning ethane or propane or anything else.
Mm.
We just have to know how many carbon atoms are in there, and we can actually start calculating the emission factor and everything else. And that's what I show here. So if we look at C8, we can calculate the molecular mass in the same way as we did before. We can calculate the carbon content, which is a bit higher because there's more carbon in relation to the hydrogen. And we can calculate an incineration factor, which means that if we burn gasoline, you definitely have to multiply by 3.1-ish. That's what your car is doing, for instance. And if we scale this up, we can actually see that it's not going to get very, very, very big. It will stay around 3.1, which actually means that if you're going to incinerate plastic or coal or something like that, it's going to be closer to 3.1.
Mhm.
And this is why burning methane is better than burning coal, because that's the difference between 2.75 and 3.1. The difference actually is super minimal. It's really bullshit. Maybe the energetic factor is, it might be a bit more efficient to burn LNG, but, you know, in terms of mass. So this is mass, basically, polyethylene. We can do it. It's a really big change to the point where we could say, like, we don't really care about the little hydrogens at the end. It's actually all just a repetition of CH2. It's one carbon with 2 hydrogen atoms, and we just repeat it. Polyethylene, we call it. Yeah, which means that we can do stuff like this, where we think about the ethylene production or polyethylene production, which is the same thing. And we can basically say, like, okay, what if you do 414 megatons of production per year, which is, I don't know where that number came from, but I think it's from our research. And then we can basically say, oh, well, that's 1.3 gigatons per year in emissions if it actually gets incinerated in the end.
Mm.
And that's gigatons. Right? This is comparable to the carbon budget, because the carbon budget is about, we were in the range of gigatons, which means that actually producing 414 megatons per year, I'm thinking this is probably the worldwide production of plastic. I see a yellow shake yes, so it's probably true. So we know that the impact of plastic production on the carbon budget is about 1 gigaton per year, which is not insignificant at all, right? It's about 1 out of 40. So we actually use up 40 gigatons per year, and 1 out of that is because we use plastic. It's not everything, obviously. There's a lot more, and a lot of it is just fuels. But plastic is not something you can dismiss, and we calculated it. Going in reserve. Um, yeah. So this is what I'm doing here is going in the opposite direction. let's say you have an incinerator, a municipal incinerator, and you know what the emissions are. You can actually calculate how much plastic or gasoline or whatever I need to go into it produce that emission. So in this case, calculating, okay, what if I have a kiloton of CO2 emissions? Well, that means you need about 3.32 kilotons, or we could do this, of course, in ton. 323 tons of gasoline would be enough to make a kiloton of CO2. We just go in the other direction. I don't need to go into the calculation in detail, but you can, if you think about it, it's just the chemistry goes backwards.
Hmm.
We can do the same thing. We count how many carbon atoms are in the emission, and we can count how many carbon atoms have to be in the fuel, and then you can count how much fuel would there need to be depending on what the fuel is. In this case, I'm using 8 C8, which is again octane or regular gasoline, more or less. But you could put ethane or methane in there as well. So if I want to do plastic, we know it's polyethylene. You need 341 tons of ethylene or polyethylene, same thing, to make a ton of CO2 emissions. Yeah, and we know for certain that that is correct because we used units. Yeah, I'm just going to show this maybe while you think about questions,
Hmm.
but I mentioned that you could use this in other ways as well. This is an example of like what we call CO2 avoidance. And this idea is, what if we replace a natural gas plant with solar panels? We can now do this calculation again by using units. You have to know that you have to think in kilowatts per hour, the actual energy output of these plants. We have to think about what the CO2 intensity is. There is a CO2 intensity associated with solar panels as well. We do the difference and so on, blah, 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 blah. And then we can actually calculate, what area would we need in solar panels to replace the natural gas plant?
Pretty cool.
Which is, one of those calculations where you're like, you always wonder, and I think a lot of journalists would, at this point, they would call an expert to do this calculation. But I'm telling you, we shouldn't actually do that. We can do this calculation ourselves. You can double check this for sure, because there are some other mistakes that you can make about just thinking about how this would work, and it's good to double check. But really, the base calculations of stuff like this is something you can reproduce, and you can double check, fact check. You can do really great things with, and it allows you to punch through bullshit anyway, right? Yeah, and that's our goal, I think here.
Amazing.
Yeah, there you
Amazing.
go.
Thank you so much, Thomas. I I mean, I've seen this presentation before. I love to see it again.
Okay,
I
yeah,
love it
yeah.
in the same way. It's very, I think it's very useful to even be aware of like that you can develop an intuition about these things.
Yeah.
That it's not just this magical um like complicated math or anything like that. That it's like
No, no.
that is very very intuitive once you know how it works.
What's
Uh,
really surprising
mm,
to me sometimes is if you think about IPCC reports, like climate reports, they always talk about emissions and emission projections, like how much are we going to emit, and people are like, how do they know that? But the thing is, like, there's a very simple way of getting a very good estimate of how much we're going to emit in the coming year, and it's basically by looking at how much is being transported. And
mhm.
that is, relatively easy to do. We can look at how much is being put on a ship to go somewhere else to be incinerated. And it's a very rough calculation, but it really tells you that there's a direct relationship between tankers and emissions and the climate. There is no broken magic somewhere. And if you talk to, you know, life cycle assessment the experts, they'll try to make it really complicated by finding all these small, the small details like, oh, this efficiency thing and blah 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 blah. But for what we do, the big impact thing, it's really nonsense. We don't need that at all. Maybe if you're comparing like two pipelines and one goes 10 degrees that way, yeah, you could talk about those differences. But from our perspective, it doesn't matter because the fact that there is a pipeline is way more important.
Hmm. Hmm. Is there any investigation that you did recently where you used this and you had like a very uh, surprising
Yeah,
insights?
yeah. So, well, actually, it was our work. Yellen and I actually published on this. I think it's still, I think people still are like very uncomfortable when we talk about it. But we really looked at what happens to plastic after it's produced, because oftentimes, climate assessments, they stop at the factory gates. Once it's plastic, it's like we don't understand what's going to happen. Now, the thing is, plastic just doesn't last forever. Like, and we were looking at, okay, what is the ultimate uh, fate of plastic? And we know that in Belgium, we're not allowed to dump it. There's no dump sites anymore for municipal waste. So the
Mm.
only other alternative is recycling and incineration. All
Mm.
these, magic waste to energy plans that they have everywhere. And so the thing is, I started calculating and I started realizing that actually recycling doesn't matter at all in terms of emissions, because the only thing it does is it briefly um,
Mm.
delays the ultimate fate of plastic.
Which is
And
incineration.
I'm
Yeah.
saying briefly because it's actually only a couple of years in total. Because most plastic is actually way shorter in duration. Most plastic is disposable plastic. If you recycle disposable plastic, that just means it's going to become waste again very quickly, right? And so the end result, that was one end result, was that actually these recycling numbers, and we already know this from other, people saying the same thing, but now we're saying it from physics perspective. Recycling is an illusion when it comes to the climate, because the recycling doesn't really do anything functionally to help abate emissions. The only thing that could is actually to avoid fossil carbon from becoming plastic.
Hmm.
If there was a magical world in which we actually had a circular model where plastic is infinitely recycled, which some people have in their head because it's the drawing that is on there, right? But that drawing is a lie. It's a complete lie. There's nothing circular about it. Our plastic is being produced predominantly, about 90% at least, from fossil fuel in pure mass. So if you think about like how much plastic is made in mass, well, 90% is fossil in origin, which means it just came directly from below us. And then there's 10% that is this little recycling loop. Now the 90% is completely dominant and it rolls over everything, and it's the 90% that produces the actual emission. And so this is the second realization that we had, is that and actually we need more investigation into this, but uh, basically the emissions from incineration plants, municipal incineration plants, is one of the biggest areas of bullshit in governmental communication that I've ever encountered,
Hmm.
because they're completely hiding the fact that we're essentially burning plastic at an enormous rate.
Mm.
You never think about this because like waste to energy and blah blah, and they're always like they also always rename it. They're like it's refuse derived fuel, something like that. But it's actually really a lot of plastic, right? And it's really a lot of fossil carbon, and it's really going into our atmosphere, and it's really one of the most carbon intensive ways of producing energy. And that's something that the BBC had also, like, I think 2 years ago, a really good report on, and they said like it's probably as bad as burning coal in terms of making energy from.
Yeah.
And so waste incinerators, when you think of it from this perspective, are one of those things. It's completely unsustainable
Mm.
in the long run. It's completely incompatible with climate change and the carbon budget and this and that. But the amount of bullshit that's around it, and that's the thing. Like, it really helped me get rid of this whole like, if I recycle, we're fine. No, if if you bought the plastic, it's already hopeless because the plastic is 90% fossil fuel anyway.
Mm.
You're not going to control that, and the ultimate fate will be an incinerator and will be CO2. And we already know this, right? There's been so much reporting on the lie of recycling, but now you see it from a very bone dry physics perspective.
Mm-hmm.
Uh, and what's interesting there is if you do that discussion with experts, they don't have the answer. Like they don't want to look at the calculation because they already know what it's going to say, right? If you know what you're dealing with, they know what it's going to say
Mm-hmm.
because you cannot hide the atoms, you cannot hide the molecular process. And I think to me that was one of those shocking revelations where I think actually, journalistically speaking, it's very difficult to publish on.
Mm.
But it's such a core finding, and the finding is that recycling is much more fundamentally bullshit than people realize. It's not just a propaganda lie, but it's a physical lie.
Mm-hmm.
And secondly, plastic production is a huge climate problem that we don't really talk about that way.
Mm-hmm. Wow. Really, really, really interesting.
Yeah.
Yeah.
It's not the only one. I don't want to say like, I'll forget about airplanes.
No,
Not at
no,
all.
no.
But like, don't
No,
forget about
cool.
this. Like, don't let them, squeeze it under the rug. Yeah.
So, you're a freelancer, right? So, where can people read your work in general? Do you have media you work often with,
Yeah.
or?
No, no. This particular thing on the incinerators was in Apache, I think.
Mm-hmm.
But we did a really big one on the industrial transition,
Mm-hmm.
as well in Knack magazine. But basically, yeah, I published on Follow the Money. If you want to read in English,
Mm-hmm.
it was mostly chemical pollution, but I publish everywhere. I'm gonna try to make it easier to track what I'm doing, but I would actually say just follow along on Blue Sky. If you think this kind of stuff is cool, drop me a line. I'm very reachable, and yeah,
I second that. Thomas is amazing.
yeah.
I will share your contact on Blue Sky under the video. Yella, do you have anything to add or any questions before we wrap up? No?
That's fine.
All right. Lovely.
We'll see each other next week.
Well,
Yeah.
thank you so much for your time and effort, Thomas. Thank you for dropping by, Yella.
Thanks for the invite.
And yeah, and I will see you around.